Okay, guys. Um, so today we're going to practice finding area. All right, area between graphs. Area, you're always using rectangles. You're summing up height times width. And we can use either vertical strips or horizontal strips. So what I want to do for the do now is just set up the integrals. We're not going to get answers. We're just going to see if we would set them up right. So like in other words, I have 5 of them. Decide whether you want to use for each one, if you want to use vertical strips, you can sit over there, sorry, or if you want to use horizontal strips. Now, if you decide you want to use vertical strips, right, so you're summing up, how do you get the height if you're using vertical strips? This being the height. Y top minus Y bottom, right? And what will the width be if it's a vertical strip? Yes, small change in it. So you'll fill in whatever Y top is, whatever the Y bottom is, equals on the bottom. And then for the limits of integration, you have to go from the smallest x to the greatest x. So when you're looking at your region, your eyes should be going, you're going to have to usually find the points of intersection, right? But you know, when it's dx, when you use vertical strips, you want to go from the smallest x coordinate to the greatest x coordinate of the shaded region. So that would be if you're using vertical strips. Yesterday we started saying, well, sometimes it's more convenient to use horizontal strips. Well, for horizontal strips, you still are going to get area by summing up height times width, but how do we get the height? Bam, x right, whatever x equals on the right, oops, minus whatever x equals on the left. Good. And what will, so that'll be x right minus x left. And what about the width? Is it a small change? It's a small change in y, right? So it's dy. Yes. Mm-hmm. Yes. You would do it, technically it doesn't matter because you could break it up. I would just clean up. If you're doing this one by hand, you're not throwing in the calculator, you're using the FTC, I would distribute the negative. If x left is a binomial, she's saying, or something like that, distribute first. Clean it up inside. Oh, yeah, I would do that. And then for the limits of integration, when you have horizontal strips, you don't want to add them up left to right. You're going to add them up bottom to top. If it's dy, horizontal strips, dy, you want to go from the smallest y coordinate to the greatest y coordinate. So you'll still get the points of intersection, but you want to use the y coordinates. You want to go from the smallest y to the greatest y. So for each one of these in the do now, set up the integral. Like in other words, integral, figure out the limits of integration. It's either going to be y top minus y bottom or x right minus x left, and either dx or dy for each one. See what you can do. Do you want to try one together, or you guys feel like you can do it? You can do it? I knew it. I don't know. Okay, so to get the first region, what do you think? We're going to use vertical strips or horizontal strips? Vertical, way to go. Now, sometimes you can do both, but usually I always say, okay, I'll try to use vertical unless there's a problem. Oops. That's just one, but really we're adding up an infinite number of them. We got little short ones, and we're adding them all up. So we're summing up. Now, to get the height, since we're using vertical strips, what do you got for the height there? Y top minus y bottom. What is y top equal? For any of these, what is y on the top equal? 5. Minus y bottom. X squared plus 1, which we have to put in parentheses, or else you're only subtracting the x squared, not the x squared plus 1. You want to subtract the whole thing. Okay, that would be the height of any one of these. Now, what is the width, since it's a vertical strip? The x, nice. Now, the limits of integration, we want to add up height times width, the areas of these rectangles, from the smallest x to the greatest x. So what are my limits of integration? -2 to 2. They're kind of nice with this one. That's it. And when they say set up but do not evaluate an integral to find the area, then you're done. Now, if you really wanted to get the answer, I'd clean it up in here, take the antiderivative, plug in the upper, lower, subtract. We'll do that, but this is just the setup. Any questions for that one? Let's do the second one. Now, what do you want to use this time? Vertical or horizontal? Let's use horizontal. It's just good fun. You could do this using vertical strips. You would have to break this parabola up into two functions, though, so y top would be different than y bottom. So we won't do that. We're going to use horizontal strips. So we're adding up a stack of these. Oh, well, it wasn't so good. Now, since it's a horizontal strip, how do I get the height? X right minus x left. Now, for any one of these, no matter where I draw it, what does x on the right equal? 4, right? Now, x left is x on the parabola. What does x on the parabola equal? Squared plus 1. The horizontal, so dy. So you notice when it's dy, the only variable I'm allowed is y. And very important, the limits of integration, smallest y to greatest y. So I'm looking at it, it's from this y to that y, but it's not clear what it is. How am I going to find out what my limits of integration are? Set them equal to each other. So you want to set, if you want the y coordinates of where they intersect, set what x equals on one equal to what x equals on the other. Because when they intersect, their x coordinates are the same. That's why you can do that. So on one, y squared plus x equals y squared plus 1. When they intersect, that must equal x on the other, which is 4. Solve that for y and tell me what you get. Plus or minus rad 3. What is rad 3 around? Can you give me a number? Like 1 point, 3 is 1 point something. You know, anyone know the 10th digit? 7 something? Okay. Not that you have to, but I just want you to see that it makes sense with the graph that they gave us. That looks like it's about 1.7 something, and this looks like it's like negative 1.7 something. But on the actual integral, we write, what do we write for the lower limit of integration? Negative rad 3, positive rad 3. When you're using horizontal strips, you only care about the y coordinates of the points of intersection. I don't need to know the x. I mean, I know the x coordinate's 4 for both those points, but you're adding them up from negative rad 3 to positive rad 3. And that'll give us that exact area. Woo-hoo. The next one, scary. What do we want to use, vertical or horizontal? Vertical. Why is this one scary? Yeah, we're going to have to add two integrals together. We'll get the area of each region separately. So, to get the area of the first region, did we say whether we're using vertical or horizontal? Vertical, right? I want to find the area of that first region, so I'm summing up. What's the height of any of those rectangles? Oh, by the way, g of x is the line, and f of x is the curvy one. So what would the height of any of these rectangles be? Yeah, for this first region here, kids at home. Yeah, f of x minus g of x, y top minus y bottom. That would be the height. What's the width for those? Yes. Yeah, sure. dx. Now, I'm trying to get the area of this first region. What are my limits of integration to get this area? B to A? Yeah, A to B. So you want to add the areas of these rectangles up starting at A and going all the way up to B. Now we have the area of that first region. We need another plus a definite integral, You want to add the area to the second region. So first thing I have to know is what is the height of any rectangle in the second region? Nice. G of x minus f of x. Dx. So the dx is important. Don't forget about that. So for my limits of integration, we want to go from smallest x to greatest x. Beta c. Just set it up. Now it gives us the total area. Now, if we wanted to do it with one integral and we had a calculator, you know what we could do? Anyone know? If I wanted to just get the total area, I'd have to put one little thing in here. I could just take f of x minus g of x dx, and I could go all the way from a to c. But some of these would have negative heights. It wouldn't give me the area. What could I do so none of the rectangles would have a negative height, so I would never have, bam. I'm not saying you're ever going to do that, but you could. Just something to think about. But yeah, this is the way you do it. Alrighty, let's try the next one. So fun. Okay, now, this next one here. Wow, we want this area, this region in here. You're going to use vertical or horizontal? Okay, because if you try to do horizontal, you would need more than one integral. Because let me just see if I can drag this guy. If you try to use a horizontal rectangle, you know, down here, x right is on this parabola, but right when it gets to that point of intersection, oh no, now x right changes graphs. So you wouldn't be able to do it with one integral. So forget that. So yeah, we'll use vertical strips. Thinking about an infinite number of them. Since we're using vertical strips, can you tell me what the height would be? Okay, I always call I know height, width, doesn't matter what you call them. When I say width, I always mean the infinitely small dimension. That's the dx. What about the height? Y top minus y bottom. Which graph is this red one? Is it the negative x squared or the x squared minus 8? Negative x squared. So y top is negative x squared. This length, and then minus y bottom, y on the blue parabola, minus x squared minus 8. Make sure you put in the parentheses if you're subtracting anything more than a monomial. Limits of integration. Smallest x to greatest x, dx. Negative 2 to 2. That'll get you the exact area. Huh? Questions? Excited about the last one, aren't you? All right, now, we want to use vertical, because assuming that maybe we're a little, well, we want to be efficient, okay? But it'd be more efficient to use vertical strips or horizontal strips? Horizontal. Because if you try to use vertical strips, you might be happy, oh, y top minus y bottom, y top minus y bottom. But once you get to this point of intersection down here, y bottom now changes from the line to the parabola down here. Now, you don't want that, because then it requires a whole other integral to get that area of that second region. So vertical is no good. We want to use horizontal. Oh, yeah, we'll get to that. So, no, that's good. You're seeing that. So we're adding up an infinite number of these horizontal strips. So area is the sum of. How do I get the height, the long dimension of a horizontal strip? Yes. Well, okay, before I do x equal, what is it, though, in general? X right minus x left. Okay. X right is x on the parabola. Okay. What does x on the parabola equal? Well, I know what y squared equals. Can you do a little mental math and tell me what the x coordinate on the parabola has to equal? move things around. What is it? 4 minus y squared? Is that right? I believe that. Okay, so x right, x on the parabola is equal to 4 minus y squared. Minus x left, you said. That's x on the line. There's the equation of the line. What does x on the line equal? 1 minus 2y. So minus 1 minus 2y. What was that? So the height is all that. And the width, dy. Limits of integration. The smallest y to greatest y of the region. Smallest y coordinate to the greatest y coordinate. -1 to 3. Yeah. Was anyone thinking -5 to something? No? Okay, good. I'm just saying, it's very, you have to, because it's dy, you're adding up this stack of rectangles starting at y equals -1. It's all about y now. And you're going all the way up to y equals 3. And that'll get you that area. Nice? Did you guys just crash? Just get tired? Oh yeah, this one, it was nice from the graph. If you had to get those y coordinates, the point of intersection yourself, you would set 4 minus y squared equal to 1 minus 2y. Oh, that's quadratic. That's ugly. Okay. What I'd like to do, I know yesterday I kind of rushed through it a little bit, but I know some people are the troopers. So I did give you the solutions to the homework, and maybe if you want to, when you get a chance, go back and look more at it. That's you. But I was thinking we could maybe go back and finish the examples from yesterday, unless you want to do one of these. It doesn't matter. It's all using parts. You okay? Take-home quiz together? Nope. Make sure when you do that take-home quiz, after you set up the integral in 6, 7, and 8, if you want to use the fundamental theorem of calculus to get the answer, great. But you are allowed to use your calculator in questions 6, 7, and 8. So if you set it up like we just did in the do now, then you can just get your answer if you want to on the calculator. Ideally, you do it using fundamental theorem of calculus and you just check your answer with the calculator. That would be the best. Then you got it all. Okay, so I do want to finish the examples from yesterday because they're just fine examples. So fine. I hate to miss them. Did we go back and try C with horizontal strips? See if in your notes if you have anything where it says C again. I might have not have got to it. Nope. No. See, this is one of those cases where you can just save yourself a little time and effort if you use horizontal strips. Do you guys remember what the graph of x equals y squared looks like? Sideways parabola. Now, I got to remember which side. Would the x's be positive or negative? Positive, because x equals the y coordinate squared. So it's on this side. Here's the graph of y equals, oops, nope, x equals y squared. I think I'll write that over here. So this parabola here is x equals y squared. Now what about the other graph? What is this going to be? Still quadratic, right? It's another parabola. What's the greatest that x can be? Because x is equal to 3 minus 2y squared minus something. Well, how great can x be? If x is equal to 3 minus 2y squared, the greatest it can be would be 3, right? So I'll go over here. Let's say that that's 3. So it goes the other way. So you have these two parabolas. This one over here is x equals 3 minus 2y. We're going to find that area of that region, but you know what I got to do first? I got to color time. Sydney? Mauve. Isn't that how she likes to pronounce it? That's pretty. Okay. Is this going to work? It's pretty on my computer screen. And Sydney, for you, I'm going to leave a couple of spots. That's 2 legs. Let's leave that there. Good? I'm sure you will. All right, so we're going to get the area using horizontal strips. Right? Horizontal strips are the way to go because you think this problem's going to be so bad, and it works out great. Horizontal strips. X right minus X left. For any strip, what is the X coordinate on the right equal? Can I unplug it? Sorry. Okay. Okay, so X right is 3 minus 2y squared. See it? Minus X left. Oh, minus y squared. Oh, that's not bad. Okay. What is the width of each? Oh, sorry, yeah. I got a little distracted. So it's dy. Okay, limits of integration. Should I say 0 to 3? No, those are the x's. We're talking y's now. We got to set them equal to each other. I want to set what x equals on one equal to what x equals on the other and solve for y. You kids do that. That's a fine place to do that. I have to do it here, really tiny. So u x on 1 equals y squared. 3 minus, so we're setting y squared equal to 3 minus 2y squared. Solve that for y. Plus or minus 1 you got? Really? Great. I'll buy that because it's right. So that's telling us when they intersect, the y coordinate down here is -1 and the y coordinate up here is +1. I don't even need to label that. I just have to write in my limits of integration. What's the lower one? -1 and the upper one is 1. Now this is just so lovely. I want to just go ahead and get the answer for this one if you don't mind. Not just the setup. So I think I'm just going to have to move it all. It's not going to work. Oh. All right. That's all right. Before I actually get the answer, I'm going to do this like... all right, I'm just erasing it. That was cool. That was very cool. We're just going to get the answer. We know what we're getting the area of. All right. What would you do first? You want to get this area. Before you integrate, clean it up. Combine like terms. Here's 1 to 1. So 3 minus 3y squared. Lovely. Okay. Now I got this integral sign. What is that reminding you to do? Yeah, integrate. Get that antiderivative. What's the antiderivative? 3y minus y cubed. Nice. And then we draw a little line, meaning evaluated from -1 to 1. Then what? Which one do we plug in first when we're applying the FTC, the fundamental thing top? Right, on the calculator you do the lower first, but when you're doing it this way, so we're going to plug in the 1 first. Oops. Plug in the 1. And then we'll plug in the -1. Okay, so what do we get for 3 minus 1 cubed? 2. Minus, what do we get when we plug in the -1? -3 plus 1. Well, you got -3 minus -1, -2, right? So it'll be a +2, yeah. Total answer, 4. It wasn't really so bad. Now let's say I didn't feel like using the fundamental theorem of calculus to get my answer. I set up the integral and I wanted to put in my calculator. If you put in your calculator, just use x's. In other words, you would just do math 9, 3 minus 3x squared, comma x. And on the calculator, what do I put first? -1, comma 1. And that should get you an answer of 4. So even though you set your integral up and it's all in y's, and that's important, if you want to use your calculator to get the answer, it doesn't know what's on your paper, just put in with x's. And hopefully that gives you 4, or something close to it. The calculator is not a calculus master like you are. Got it? Yeah. Let's try another one. I just want you to see a few of these. Can we set this one up without going to the calculator, just from your awesome knowledge of what graphs look like? Maybe. Maybe. Well, what about with the square root of x? Show me square root of x, kids. That was good, but you just went downhill at the end there. You gave me like a semicircle. You were doing it. Okay, that was better. All right, square root of x. Let's graph this. That's it. Y equals negative x plus 6. What does that look like? Yeah, it was good. Nice. It's a line. The slope is -1. The y-intercept is 6. That was exciting. I'm trying to make it exciting. And then the last one, y equals 1. Throw that in. Let's see. So I got, so this region enclosed by all 3 of those. Color time. Nope. What color am I picking? Is that fairy one? No, what is that fairy one? You want this one? This? All right, I'll do some. Extra, well, bring your own markers. Pretty. Oops, sorry, Sid. Oh, look at this, the overlap color. For some reason it does that now. Okay, so you look at this. Do you want to use vertical strips or horizontal strips? You use horizontal strips. Because I don't see if you use vertical strips, wide tops, fine, fine, fine. Oh no, when you get here, it switches graphs. So you'd have to have a separate integral to get the area over here if you use vertical strips. Anytime in general, you're going to get area. If you see a point of intersection, like on the top, you're going to want to use horizontal, or on the bottom, you're going to want to use horizontal. That's just what I look for. Forget that. Okay, drawing in my representative horizontal strip. There it is. Present them all. Area is always the sum of height times width. We've chosen horizontal. Yeah, we do. Let's get the height. How do we get the height of a horizontal strip? X right minus x left. So I got to find out what x is on this, on the line. Okay. Oh, here's the line. What does x equal if you're on the line? 6 minus y. Okay. So if you're on the line, the x coordinate equals 6 minus y. Good. Minus x left. X on the graph of y equals rad x. Well, if you're on the graph of y equals rad x, what does x equal? Y squared. So you had to square the whole side. Woo! What's the width? dy. Better be. You see 2 different variables, you're in trouble. You are in trouble. Limits of integration. Yeah, you see that the lower limit of integration, we know this is the line y equals 1, and we are adding them up from 1 to something, but I got to get to something. Okay, but we do know the lower limit of integration is 1. So we got to set them equal. And if you want the y coordinate of a point of intersection, set what x equals on one equal to what x equals on the other. I guess I'll do that right here. So on one of them, x equals y squared. On the other graph, x equals 6 minus y. Quadratic. So what do? Before you can factor, get them all on one side. Get it equal to 0. Factoring's only good when it equals 0. So y squared plus y minus 6 equals 0. So y positive 3 you said, and y minus 2. Now, this is telling you that they intersect when when y is negative 3 and y is 2. You are going to use the 2. Does anyone know why I'm getting this other answer of y equals negative 3? Yeah, but when I squared both sides, I'm talking about now the whole parabola. And if you continued this parabola down, the y coordinate where it would hit the line would be negative 3. So we're not using it, in case you were wondering why we got that other answer. There we go. There we go. I think I want to fill in my summary. Do I have time to set up a picture for the other one? Sure. We'll just set it up. We'll do fast. We'll go fast. X equals y squared. You know what that looks like? Yeah, parabola on the side. You guys are getting better. I know, love it. Love it. Line y equals x minus 2. Got it. I'm going to forego the coloring this time. We're on a budget, time budget. All right, are we going to use vertical strips or horizontal strips? Horizontal, because it's on the notes from the horizontal strip. Okay. This is it down here. So yeah, we're going to add up an infinite number of horizontal strips. X right minus x left. X on the line, that's my x right. What does x on the line equal? Y plus 2. X left, that's x on the parabola. What does that equal? dy. Limits of integration. Ooh, we got to see where they intersect. We need to know what the y coordinate is here and here. So we set y squared equal to y plus 2. Right? So y squared minus y minus 2 equals 0. It's quadratic. You always want to get it equal to 0. And we factor y minus 2y plus 1. And our limits of integration, we got them. So from negative 1 to 2. Negative 1 to 2. So exciting. All right, now I want to fill in the summary. Got it? We can do it. To find the area between two curves, sum up the areas of an infinite number of blank or blank rectangles. What are the only two types we can use? Vertical or horizontal. Horiz. Every single time, whether we're using horizontal or vertical strips, we always are summing up the product of height times width. Good. When using vertical strips, how do you get the height? Y top minus y bottom. And the width is always yes. And the limits of integration are the smallest blank to the greatest blank of the shaded region. X. Yeah, I got the smallest x. Your eyes got to look left to right. When using horizontal strips, the height is x right minus x left, and the width is dy. The limits of integration are the smallest blank to the greatest blank. You guys are so good. Make sure you read the directions on the homework. The first 3, no calculator to do them. He's a U sub on 3. Yeah, but you can use, yeah, you'll see U sub and you get to 3. The last 3 after you set up the integral, if you want to use a calculator to get it or to check, go ahead.